In this video, we are going to talk about our first application of residues, which is evaluation of improper integrals. And the interesting thing about this is the improper integrals will be functions of real variables, but we're going to move into the complex plane so we can use residues, and that way we can get these integrals. So these are integrals that, well, except with maybe a few simpler examples, these are integrals you might normally have to go look up in a table or do some other painful thing, but now we can go and move to the complex plane and use residues. So this is our overview slide, which we'll spend about 5 minutes or so going over before we go over each topic in more detail and with more examples. The first thing we'll talk about is reviewing from our first year calculus what an improper integral is. So an improper integral is one where the limit of integration is infinity. So we could have something like negative infinity to infinity, or 0 to infinity, or negative infinity to 0. Those are all improper because one of the limits is infinity. And what we did in first year calculus is we replaced the infinity with the variable r and then took the limit as r approaches 0 of 0 to r f of x dx. So we did the integration with the limit as r, and we did the antiderivative and plugged in r, and then we would take the limit as r approaches infinity. If the limit exists, then we said the limit converges. And then we did something similar when we went from negative infinity to infinity. We just had two variables, negative r1 and positive r2, and we took the limits as r1 and r2 approached infinity. Our new material starts with the Cauchy principal value, abbreviated PV. And when we have this improper integral, that is the limit as r approaches infinity of the integral negative r to r f of x dx, we would say if the integral converges, it converges to the Cauchy principal value. But it doesn't always converge. So whatever this limit is, we would consider that the principal value of the integral of the function f of x dx. And we have this warning. Just because you can calculate the principal value, this does not mean the improper integral converges. And an example is if we have the integral from negative infinity to infinity of x dx, then the principal value of this integral is equal to the limit as r approaches infinity of the integral negative r to r x dx. Now taking this antiderivative of x, we get 1/2 x squared, and then plugging in our limits of integration r and negative r, we get the limit as r approaches infinity of 1/2 r squared minus r squared, which is equal to the limit of 0, which is equal to 0. So this is what we consider the principal value. However, we also have to check, just because we can calculate this value, it doesn't mean the improper integral converges. And so we'll look at that a little more detail when we do the full discussion in our main part of our video. The next big topic we will cover is using the residue theorem to compute an improper integral. And before we do this, we have to have the following conditions met. First, our function f of x, and in this case, this x, it's important that you notice this is not a z, which would suggest complex numbers, but it's an x, meant to suggest this is a function with real variable x. So f of x is a rational function. F of x is equal to p of x over q of x. 2, p and q have real coefficients and no common factors. 3, the degree of q is at least 2 or greater than the degree of p, but this can be relaxed later. And 4, q of z has no real zeros, in other words, no zeros on the real number line, but it has at least one zero above the real axis, in other words, an imaginary, a zero with an imaginary portion. Once we have those conditions met, we can use these steps to use residues to evaluate these improper integrals. The steps we are going to take to use residues to evaluate improper integrals starts with replacing f of x with f of z. In other words, the real number line, that is the x-axis, is part of the complex plane. So we can just replace f of x with f of z, and you can still limit your input, your variable z, to be along the real number line. But we'll look at it now. To do this improper integral, we'll look at it as part of the imaginary plane. Now that we have f of z, we're going to consider our rational function. We're going to look at the denominator q of z, and we're going to find all the zeros of q of z. That's exactly where our f of z is going to have singularities. So we'll look at all the zeros of q of z, and in particular, we're going to find the zeros above the real axis. In other words, those are all the zeros with positive imaginary parts. The next step, we're going to set up a closed semicircular contour C to integrate f of z over. So C is going to be composed of C1, and that's going to be the line from negative r to r on the real axis, and then CR, the semicircle, and here r stands for the radius, which is also the radius on our real number line from negative r to r. And the radius r here on this semicircle needs to be large enough to encompass all the singularities over here that have positive imaginary parts. Then we can apply the residue theorem, because now we have a closed contour integral. And remember, the Cauchy residue theorem says if we have this closed contour, then the integral along the closed contour is equal to 2 pi I times the residue enclosed in the contour. So we're not worried about singularities below the real number line, but only the ones above the real number line. So it's 2 pi I times the residue enclosed by the contour. And this is going to equal to, now because our closed contour is 2 parts, it's going to be equal to the line from negative r to r, f of x dx, and we'll talk about the fact that I changed back to x here, plus the contour over here, the semicircle, c sub r f of z dz. So initially I would probably write a z here and a z here, but I wanted to emphasize here along this axis, along the real axis, we are dealing with real numbered variables, which is why I can write this as f of x dx, because this will be correct as long as we're going along the real axis. So this highlights the fact that here is going to be our integral, our improper integral of a real valued function, but we related it to our residues here along with the curve that goes over this circle. Then I have this theorem, and this is from our chapter on zeros and poles. Let functions p and q be analytic at a point z naught. If p of z naught is not equal to 0 and q of z naught is equal to 0, but q prime of z naught does not equal to 0, then z naught is a simple pole, and we have this formula for the residue at z equals z naught of our quotient p of z, q of z, and the residue is equal to p of z naught divided by q prime of z naught. So we have this first example here. We have the improper integral from negative infinity to infinity, 1 over x squared plus 1 dx. And again, this is a real valued function. But now we're going to move to the complex plane, so we're going to replace our x's with z. So our p of z in this case is equal to 1, our q of z is equal to z squared plus 1. Again, this is just looking at our decomposing our function into a denominator and a numerator. We can see that p and q over here have real coefficients and no common factors. We can see the degree of q is at least 2 or greater than the degree of p. And then finally, q of z has no real zeros, but has at least 1 zero above the real axis. So to do this, I set q of z equals z squared plus 1 equals 0, and I see that this has a 0 at z naught equals I, right? When z equals I, this becomes 0. And z equals I is above the real axis. So now I can set up my integral. So I have an integral around this entire, and I redrew my line, entire closed circle. And then I'm going to integrate along the line, and I'll integrate along the semicircle on top, c sub r. And in this case, as long as r is greater than 1, we're going to capture this one singularity. The next thing I did, remember here, because we're integrating from negative to r to r, we're on the real number line, the x-axis. So I can replace my z's with x's here. I still have my integral along the top. And this is equal to, by our residue theorem, this whole closed curve integral is equal to 2 pi I times the residue. I plug into, or I use this formula here from zeros and poles theorem, and I get 2 pi I, 1 over 2I, so that's equal to pi. And I'll do this calculation in more detail later in our video. So now we have this, the integral from negative r to r, 1 over x squared dx, is equal to pi minus the limit as r approaches infinity, this integral along the top curve c sub r, the semicircle c sub r. And what we will see later in this video when we go over this problem in more detail is that as r approaches infinity, this integral will approach 0. So it goes to 0, which means that our integral from negative infinity, 1 over x squared plus 1 dx, is equal to pi. So that's our overview, and now we can start back at the top, go over all these points in more detail and with an additional example. As I had mentioned, we are going to start by looking at improper integrals as we looked at them in first year calculus. So if we have the integral from 0 to infinity f of x dx, we define that to be the limit as r approaches infinity, integral from 0 to r f of x dx. And if the limit exists, then we say the integral converges. Then similarly, if f of x is continued for all x and the limit exists, we can define this integral here where the integral goes from negative infinity to infinity, f of x dx. That will be equal to the limit of r as r1 approaches infinity of the integral from negative r1 to 0 f of x dx plus the limit as r2 approaches infinity, the integral from 0 to r2 f of x dx. I'm going to keep these notes on improper integrals that we just discussed over here for your reference, but I made them smaller so we have more room. The next thing we want to talk about is the Cauchy principal value, which denote with PV. So if we read this, this says the principal value of the integral negative infinity to infinity f of x dx. So again, it's the principal value of this integral. And we define that to be, for this improper integral, as the limit as r approaches infinity from negative r to r f of x dx. So it's just the same idea that we have from first year calculus. We replace the infinities with a variable and then take the limit as r approaches infinity. So if the integral converges, it will converge then to the principal value, this Cauchy principal value. But you should realize or be warned that the integral doesn't always converge. So just because you can calculate the Cauchy principal value, this does not mean the improper integral converges. We will do some examples showing you where this is the case, that it does not converge, and then we'll do an example showing when it does converge. Our first example is to compute the Cauchy principal value of the integral from negative to infinity x dx. So we can define then our Cauchy principal value of this integral as the limit as r approaches infinity, integral from negative r to r x dx, which is the limit as r approaches infinity of 1/2 x squared, which we evaluate at r and negative r, which is the limit as r approaches infinity, 1/2 r squared, plugging in our r here, and then plugging in negative r, we get r squared, which is the limit as r approaches infinity of 0, which is equal to 0. So this looks great. We've calculated our Cauchy principal value for this improper integral. However, what we really should have done is taking the limit as r1 approaches infinity, the integral from negative r1 to 0 x dx, plus the limit as r2 approaches infinity, the integral from 0 to r2 x dx. Remember, this is how we define this when we talked about this from first year calculus. But this is not the definition of the Cauchy principal value. The Cauchy principal value has a very clear definition, but this is really how we should be doing this integral. And you can see then that will give us the limit as r1 approaches infinity, 1/2 x squared from 0 to r negative r1, plus the limit as r2 approaches infinity, 1/2 x squared, 0 to r2. So here we're going to get a infinity minus another infinity, which is undefined. So here is our example where we can calculate the Cauchy principal value, again using this particular formula for Cauchy principal value, but we see that the integral, the improper integral from negative infinity to infinity of x dx does not converge. We're going to move up our work from our last example here so we can compare that to our next example here, which is where the Cauchy principal value does converge. And this example is that improper integrals that are even functions. So when we have an even function where f of x is equal to f of negative x, these improper integrals will always converge to their Cauchy principal value. By symmetry, if we only look at on the real axis, the negative real axis, so we're going to integrate from negative r1 to 0 f of x dx, that's going to be exactly half of integrating from negative r1 to r1 f of x dx, again because we have this even function. Similarly, if we go just the positive half, 0 to r2 f of x dx, then that's going to equal to 1/2 negative r2 to r2 f of x dx. So now using kind of our correct definition, so to speak, where we divide up the integral from r1 to 0 f of x dx plus 0 to r2 f of x dx, we let the limit of r1 and r2 go to infinity, then this, by symmetry, is equal to 1/2 the integral from r1 to r1 f of x dx. This, by symmetry, is equal to 1/2 r2 to r2 f of x dx, which is equal to 1/2 then the antiderivative of f of x, evaluated at r1 and negative r1, and 1/2 the antiderivative of f of x, evaluated at r2 to r2, which is going to equal to 0. So in this case, our Cauchy principal value is going to equal to the integral from negative infinity to infinity, f of x dx, and our integral converges. Our next topic will be using the residue theorem to evaluate improper integrals. We are going to use this example to illustrate how to use these steps. So we're going to evaluate the improper integral from negative infinity to infinity, 1 over x squared plus 1 dx. And the important thing to notice about this is an improper integral of a real function with real variable x. Here, we plug in this x is to suggest that our variables are real, and when you plug it in, you get a real number. So it's a real function with a real variable x. So this is similar to an integral you might have found in first year calculus. But in first year calculus, you learned all these techniques of integration to do this. But now that we're in complex analysis, what we're going to do is transform this integral into an integral in the complex plane. And certainly the complex plane contains the real axes that this integral is performed on, which is why I can claim this is a valid thing to do. And the first thing I'm going to do now is replace my f of x with f of z. So I'm going to be looking at the integral negative infinity to infinity, 1 over z squared plus 1 dz. And again, the implication is now z is a complex number, so I've moved this into the complex plane. But of course, real numbers are complex numbers with the imaginary part equals 0, so I can stick to plugging in real numbers into this function as well, into my complex function, and I'll get the same thing as my real function with real variable inputs. So this, again, another way I'm just trying to justify that this is an okay thing to do. Before I go on, I want to mention in my overview slide, I said that we have these conditions. This is this part of our overview slide that needs to be met before we use residues to evaluate improper integrals. So let's check these conditions out for our example. I went ahead and copied those conditions here for our reference. So first, we're going to be looking at our function as a rational function. So here, I'm going to look at p of z is equal to 1, and q of z, our denominator, is equal to z squared plus 1. We see that p and q over here have real coefficients and no common factors. Second, we see that q is at least 2 or greater than degree of p, right? This is a second order polynomial, and this is a 0 order polynomial. And q of z has no real roots, but has at least one zero above the real axis. So in particular, when I set q of z equal to 0, we see that q of z has a root at z naught equals I. So I is not a real root, but it is a root that is above the real axis. So in the complex plane, right, our I variable here, it's above the real axis over here. So we see that all the conditions here are met. I'm going to move our notes about P of z and Q of z up here so we have more room. And the next thing we want to do is we're going to set up a closed semicircular contour to integrate f of z over. So C, our closed contour, will be composed of C1 that goes from negative r to r over here. And then that's on the real axis. And then CR is going to be our semicircle over here. And the radius must be large enough to encompass all the singularities. So here, as long as the radius is greater than 1, we're going to enclose our singularity that's equal to I. The integral over the closed contour C, and again, C is the entire closed contour, the semicircle and the line, is equal to the integral over the line plus the integral over the top half of the semicircle. Now this is where I'm going to observe that when I'm on this line from negative r to r, I'm on the real axis. So I'm going to emphasize that now by changing my z's over here to x's. So I'm going to integrate from minus r to r, 1 over x squared plus 1 dx. And I can do this because, again, this part of the line is just the real axis. And I'm going to tell you I emphasize this because I distinctly remember as an undergraduate writing this down and then later looking at my notes and being like, hey, wait, what happened here? How did I go from z, the complex numbers, to x? And it took me a while to realize, oh, that's because I'm on the real axis. So, my confusion, I still remember that confusion, but now I take pains to explain it to you. And the thing about this closed contour integral is we can apply the residue theorem. So remember Cauchy's residue theorem that says if we're taking an integral over a closed contour, that's equal to 2 pi I times the sum of the residues that's enclosed by the contour, right? If there's a residue out here or somewhere outside the circle, we don't care about those residues, only the residues enclosed by our curve. But we did choose our curve in order to enclose all the singularities that are above the real axis. And to calculate the residues, remember that chapter we talked about calculating residues? This is why. So you might want to go back, see what there is to calculate the residue. But here we have z equals I. That's a simple pole. So we have this theorem from the zeros and poles part chapter of residues that it said if we have a function that's a quotient of two other functions, p and q, so we have two functions p and q that are analytic at a point z naught. If p of z naught is not equal to 0 and q of z naught is equal to 0, in other words, we have our singularity, and q prime of z naught does not equal to 0, then z naught is a simple pole of the quotient, and the residue at z equals z naught of our quotient is equal to p of z naught divided by q of z naught. So here is our quotient. Our p of z is equal to 1. Our q of z is equal to z squared plus 1. So p of z is not equal to 0 because it's never equal to 0. Q of z is equal to 0 at z naught is equal to I. But q prime of z naught, which is equal to 2x, does not equal to 0 at z naught equals I. So our residue at z naught equals I of 1 over z squared plus 1 is equal to p of I divided by, here it is, q prime at I. So it's 1 over 2i, which is equal to 1 over 2i. So I'm just going to add this over here. So this is 2 pi I times the sum of the residue, which is just 1 over 2i. There's only one residue. So that's equal to pi. So now what I have, I'm going to start with this here. I have, and I'm going to write the limit as r approaches infinity. of our integral negative r to r 1 over x squared plus 1 dx is equal to, on this side of the equation, we have pi, right? We calculated that using the residue theorem. So we have pi, and then we're going to bring this, subtract it both sides of the equation. So we have limit as, or minus the limit as r approaches infinity, the integral c of r, 1 over z squared plus 1 dz. At this point, we're going to show that this integral here, as r approaches infinity, that this integral approaches 0. So that's this note over here we have in blue. So again, here we have our radius r, and r is going to infinity because we're integrating from negative infinity to infinity. So also this radius is going to infinity. And we're going to show that this goes to 0. For now, I'm going to take it as given, but this will be the last step that I do, is show that this approaches 0. And that means our final answer is this improper integral from negative infinity to infinity of 1 over x squared plus 1 dx is equal to pi minus 0, which is equal to pi. So this is our final answer for this improper integral of a real function with real variables. And now I need to come back to this over here where I claimed that this integral over the upper half circle, as r approaches infinity, the integral will approach 0. So I'm going to clear some of this out, and I'll move this up so that I have some space. Here I have some of the key steps. Our closed curve integral equals the integral over the real number line plus the upper half semicircle, and this, because it's closed curve, is equal to 2 pi I times the residue, which is 2 pi I times 1 over 2I is equal to pi. And then again, the step I wanted to show is that this portion, this integral over the closed curve integral, approaches 0 as r approaches infinity. And what we are going to use is this theorem here from the chapter on moduli. And this is a section that I unfortunately skipped. I did the whole chapter except this one section, but that's okay. I'll show you the theorem here. We'll give it a brief explanation, and then we'll use it. So the theorem gives us an upper bound for the moduli of a contour integral. And here we have a contour integral. We're going to look at its modulus, the absolute value of the contour integral f of z dz, and we're going to show it has an upper bound. And by bounding it, we have some hope in showing that it approaches some number. So let's denote a contour of length L. In this case, for our semicircle of radius r, well, the circumference of our circle, so the length of our circle, is going to be diameter times pi, but since we only have the upper half, it's going to be 1/2 diameter times pi, or in other words, it's going to be the radius times pi. And let me go ahead and make that note. For our circle, L is going to be the radius times pi. The next thing we have is suppose that a function f of z is piecewise continuous on C. So in this case, our f of z is 1 over z squared plus 1. So it's continuous everywhere except for the singularity at I. But because our circle radius is greater than 1, our function f of z is continuous everywhere on our semicircle. So we're good there. Next we say if m is a non-negative constant such that m is greater than or equal to all absolute value of f of z for all points z on C, which f of z is defined. So in other words, if we can find a non-negative constant m that's greater than all our f of z, so our m kind of is the capital M, is sort of supposed to suggest the idea that it's a maximum. So if we can find a maximum value for all the absolute values of f of z, then what we are going to conclude is that this integral, the absolute value of the integral, is less than or equal to m times L. To give you some intuition what this is about, remember in first year calculus when we did integrals, if we had a function f of x, so f of x or y is a function that depends on our variable x. When we integrated over this curve, what we were doing was we were summing up all the heights, all our values of f of x along the curve from A to B. And in that way, we could get the area underneath the curve. So this is similar to what we're doing here. Here, we're summing up all the f of z's along a path. And if we know the maximum value of any f of z on this path is equal to m, then we know when we sum up all our values of f of z that that's going to be less than or equal to our maximum value times the length of the curve. And the analogy over here, if we know that this is our maximum value of f of x, when f of x goes from a to b, then the area under the curve is going to be less than or equal to f of x, our maximum f of x, times the length of our interval. Applying now this theorem to our integral here. So we have the modulus of our integral over CR of f of z dz is less than or equal to our maximum value in this radius times pi r being the length of half of our semicircle, or half of our circle, or length of the semicircle. The next step is to consider the modulus of z. If z is on our circle, then the modulus, or the radius, the distance from the origin, is going to be equal to r. So modulus of z squared is equal to modulus of z squared now, which is equal to r squared. So then our denominator here, where is this, z squared plus 1, the modulus of z squared plus 1 is going to be greater than or equal to the modulus of z squared minus 1, which is equal to r squared minus 1. Which means for all points z on CR, the modulus of f of z is going to be equal to the modulus of 1, which is just 1, over the modulus of x squared plus 1, which is going to be less than this maximum, mr, where mr is equal to 1 over r squared minus 1. Finally, we use our theorem. So the modulus of this integral here, now this is the integral we're interested in seeing go to 0, is less than mr pi r, according to our theorem, and mr over here we just calculated is equal to 1 over r squared minus 1. So mr pi r is pi r squared minus 1, which you can see approaches 0 as r approaches infinity, since the exponent on bottom is greater than the exponent on top. This is how we finished this problem, but I do have two things to comment on. The first are these conditions here that we wanted to satisfy so that we could use our technique. And the condition that we're going to look at here is the degree of Q is at least 2 greater than the degree of P. In our example problem, when we used our theorem and we looked at the modulus of f of z, so we replaced our x squared with z squared, and then on this curve, the modulus of z is equal to r. So wherever we had an x, we would replace it with an r. So what we needed, if this is our mr, and then we're going to look at the modulus of the integral, so we need to multiply it by the length. And over this semicircle, the length is always going to be pi over r. So what we needed for this to approach 0 as r approaches infinity is we needed the exponent on the r in the denominator to be greater than the exponent of the r in the numerator. And that's why the degree of Q has to be 2 or greater than the degree of P. And it was not sufficient just to be greater than the degree of P, because we're multiplying by this other factor of r that we get from the length of the curve. So it has to be 2, at least 2 greater than the degree of P. The second comment I had is when we set up this circle with radius r, one of the things we said we wanted to happen is the radius had to be large enough to encompass all the singularities, and the reason for that is we used Cauchy's residue theorem. And remember, for Cauchy's residue theorem, C is a simple closed contour, positively oriented. If a function f is analytic inside and on C, except for a finite number of singular points inside C. So in other words, we need f to be analytic on C. We can have finite singularities inside C, but we don't want C to have any singularities, and that's why the radius r has to encompass all the singularities. It can't have a singularity on our curve. Okay, now we have the big picture. We can do our next example, which is to evaluate the improper integral from 0 to infinity of x squared divided by x to the 6th plus 1 dx. I start by looking at f of x as a rational function p of x over q of x. So p of x then is equal to x squared and q of x is equal to x to the 6th plus 1. We see that p and q have real coefficients and no common factors. The degree of q is at least 2 or greater than the degree of p. And then last, q of z has no real zeros. There's no real number that we can plug in for x and get a 0 for q of x. But we can find one 0 above the real axis. What I have then is q of x equals x to the 6th plus 1. I set that equal to 0, meaning that x is equal to the 6th root of negative 1. Remember, to find the roots of complex numbers, generally what we do is we're going to take this number negative 1, convert it into our exponential form, and then we'll take, in this case, 1/6 of that number. So negative 1 is radius of 1, and then the phase, or the angle, is equal to pi, right? So we go over pi radians to get to negative 1. So negative 1 is equal to e to the I pi. But you have to remember that we can keep looping around 2 pi. We can add 2 pi to that a number of times and get another root. So our 6th root is e to the I pi plus 2 pi k, which means our 6th root is equal to e to the I pi over 6 plus I 2k pi over 6. We will see then that we're going to get 5 zeros. So we're going to plug in k, actually we get 6 zeros. K equals 0, 1, 2, 3, 4, and 5. So we'll start with k equals 0. That's nice, we get e to the I pi over 6. For k equals 1, we're going to get e to the I, then this is going to be 2 pi over 6 plus pi over 6, so we're going to get 3 pi over 6. For k equals 2, we're going to get 4 pi over 6 plus pi over 6, which is 5 pi over 6. For k equals 3, we're going to get e to the I 7 pi over 6. K equals 4, we're going to get I 9 pi over 6. K equals 5, we're going to get I 11 pi over 6. Now when we plug in k equals 6 now, you'll see that we get e to the I pi over 6 plus I 2 pi. In other words, we've come back all the way around to e to the I pi over 6. And you'll notice that q of x has no real zeros. In other words, none of these numbers here are on the real number line. This drawing was for when we were illustrating negative 1. But e to the I pi over 6, right, our angle is going to be somewhere here. So it's above the real axis. Here, 3 pi over 6 is going to be somewhere here. Above the real axis, 5 pi over 6 will be here. 7 pi over 6, that's more than pi. So it's going to be below the real axis. 9 pi over 6 is below the real axis. 11 pi over 6 is below the real axis. So we have 3 zeros above the real axis over here and 3 below the real axis. And now I'm going to note that here, q of z has 3 zeros above the real axis. I wrote what they were, and I kind of drew them approximately where they would be in our circle. And then up here, I put our steps to use residues to evaluate improper integrals. So this is step 1. We found all the zeros, q of z, above the real axis. Step 2, we're going to set up our closed semicircular contour C to integrate f of z. So C will be composed of C1, the line between negative r and r along the real axis, that's here. And then C of r, the semicircle. So this is our C of r. I guess I should label that C of r. And in this case, here's our 3 singularities. They all have radius of 1. So as long as r, our radius here for our semicircle and our closed contour, is greater than 1, and I have that noted over here. So r needs to be greater than 1. then we can encompass all the singularities. Now I'm going to write my formula. So our closed contour, C, that's this whole contour that's closed, is equal to the contour over the real number line plus the contour over the semicircle, this top half, C sub r. And now we can apply the residue theorem. This part here is our closed contour, and by Cauchy's residue theorem, that's going to equal to 2 pi I times the residue of the singularities inside this curve. And I went ahead and wrote down Cauchy's residue theorem here for your reference. Let C be a simple closed contour, positively oriented if a function f is analytic inside and on C, except for a finite number of singular points inside C, then the closed contour integral is equal to 2 pi I times the sum of the residue, where the k goes from 1 to n, and those are our singularities inside the curve. And the residue, if you recall, is equal to the B1 coefficient in our Laurent series expansion. That's the coefficient above the z minus z naught to the minus 1 term. Okay, so I factored out my bottom z to the 6th plus 1 with my 1, 2, 3, 4, 5, 6 singularities, but I realized actually I didn't need to do this. But you know what? This took me some time, so I put it there in case you did it and you wanted to check it, and maybe you had a different theorem you used to calculate the residue. But I'm going to use this theorem here from one of those chapters when we talked about how to calculate residues of poles. So this is from zeros and poles. The theorem says let two functions p and q be analytic at a point z naught. If p of z naught is not equal to 0 and q of z naught is equal to 0, but q prime of z naught does not equal to 0, then z naught is a simple pole of the quotient p of z over q of z, and the residue at z equals z naught of p of z over q of z is equal to p of z naught divided by q prime of z naught, and that's what we're going to use here. Actually, and as I said, I didn't need to calculate this. But it was so much work, I had to show it to you. So I didn't copy the whole theorem, but I copied down the formula for the residue at z equals z naught of the quotient is equal to p of z naught divided by q prime of z naught. Over here, p of z then is equal to z squared. Q of z is equal to z to the 6th plus 1. So I have q of z, z to the 6th plus 1, then q prime of z. If I take the derivative of this, I get 6z to the 5th. So p of z divided by q prime of z is equal to z squared over 6z to the 5th, which is 1 over 6z to the 3rd. So now if I want to calculate my residue at c naught equals e to the pi over 6, I pi over 6, that's my first singularity of z squared over z to the 6th plus 1, that's equal to 1 over 6, then z cubed. That's my e to the I pi over 6 cubed, which is 1 over 6 e to the I pi over 2. E to the I pi over 2 is simply equal to I, right? You come up over pi over 2 radians, radius 6. So you have 1 over 6 I. Our next residue is for our next singularity, which is e to the I 3 pi over 6, which is equal to e to the I pi over 2, which is just equal to I. So the residue at I, plugging into our formula here, 1 over 6z cubed, is 1 over 6i cubed, which is equal to negative 1 over 6i. And then the last residue for e to the I, 5 pi over 6, plugging into the formula of 1 over 6z cubed, is equal to 1 over 6i. Which means now that our closed curve integral is equal to 2 pi I times the sum of the residues that are inside the curve. That's 2 pi I times 1/6 I minus 1/6 I plus 1/6 I, which is simply equal to pi over 3. And now this closed curve integral we found from the residue, Cauchy residue theorem, is equal to pi over 3, and it's equal to, over here, just bringing this down, first our integral from negative infinity to infinity, and now because this, when we're on the real line, we can replace z with x squared over x squared plus 1 dx, plus our integral over the curve c sub r, z squared over z to the 6th plus 1 dz. And as we noted, this closed curve integral, it's not closed curve, the integral over c sub r as r goes to infinity approaches 0. So we're going to let that go to 0, and we're going to look at that in just a minute. But before we do, we're just going to finish the problem because we're so close. So that means this integral here, well, actually our original problem was from 0 to infinity. So we just need to take half of this integral from 0 to infinity, x squared, x to the 6th plus 1 dx is equal to pi over 6. And we can do this where we just take half because this is an even function. Okay, now that we finished that problem, we're going to come back and look at this and see why this integral, when we're on this upper half circle, as r approaches infinity, this integral goes to 0. Much like our other problem, we're going to observe that the modulus of z, when we're on this curve, c sub r, the modulus of z, or the radius of z, is going to be equal to r. So the modulus of z squared is going to be equal to r squared. And then looking at this denominator, then the modulus of z to the 6th plus 1 is greater than or equal to the modulus of z to the 6th minus 1, which is equal to r to the 6th minus 1. And again, like we did for our previous example, we're going to note for any point on our curve c sub r, the modulus of f of z now is equal to the modulus of z squared, modulus of z to the 6th plus 1, which is going to be less than our maximum value on the circle, where the maximum value is equal to r squared divided by r to the 6th minus 1. By our upper bound for moduli of contour integrals theorem, this will imply the modulus of the contour integral on r, f of z dz, is going to be less than or equal to mr times the length of this curve. And we had noted the length of the upper semicircle is pi r. And now we can plug in our mr for this function. So continuing, mr pi r is equal to pi r to the cubed over r 6th minus 1, which approaches 0 as r approaches infinity. So we have this upper bound that approaches 0. That means our contour integral becomes 0. Okay, that wraps up the main portion of our video. And to review what we have covered, we talked about evaluation of improper integrals. And in particular, we looked at improper integrals involving real functions with real variables, but we took them into the complex plane so that we could then use our residue theorems to evaluate those improper integrals. And it was valid to do that because along the real number line, when you have your real functions and real variables, well, that real number line is still part of the complex plane. The real numbers are just complex numbers where the imaginary part is 0. So we're able to take it into the complex plane, use our residue theorem, and then we can come back and figure out what our integral was. So the first thing we did is we reviewed improper integrals from calculus, and we said that if we have an integral from 0 to infinity, for example, f of x dx, we would define that to be the limit as r approaches infinity, the integral from 0 to r now, instead of infinity, f of x dx. And we did something similar where we had the integral from negative infinity to infinity, and that we let r1 approach infinity, and that would be our bottom limit, and then we let r2 approach infinity, and then r2 would be our top limit. These limits don't always exist, but when they do, we say the integral converges. So similarly, we defined the Cauchy principal value of an improper integral. So we denote it with the PV. So when we have an improper integral, we can take the principal value of the integral, and we define that to be equal to the limit as r approaches infinity of negative r to r f of x dx. Notice this is not the same thing that we had talked about here with the real numbers, where we divided it up into the negative r to 0 and 0 to r2. The principal value just takes a single number r approaches infinity, and then the integral from negative r to r f of x dx. So with that, there's a warning. Just because you might be able to calculate this Cauchy principal value, it doesn't always mean that the improper integral converges. And we did an example where we calculate the Cauchy principal value, but the integral does not converge. And then we had an example that is even functions, where they always converge to the principal value. The next topic we covered was using the residue theorem to compute an improper integral. And the first thing we had were these conditions that had to be met. We had to have our function be able to be written as a rational function p of x over q of x. And p and q had to have real coefficients and no common factors. The degree of q had to be at least 2 or greater than the degree of p, and q of z could have no real zeros, but have at least 1 zero above the real axis. And then what we did is we followed these steps to use residues to evaluate the improper integral. First, we replaced f of x with f of z. And as I mentioned, now f of x is a real valued function. X implies that we're on the real number line, but the real number line is part of the complex plane. So we can certainly look at this in a broader view of a complex function with the understanding that we're only plugging in real values x, but we can still look at it in f of z. So then we find all the zeros of q of z. In this case, q of z is the denominator above the real axis. So we're concerned with the zeros with positive imaginary parts over here. We set up a closed semi-contour C to integrate f of z, and C is going to be composed of C1, which is a line between negative r and r on the real axis, and CR, which is the semicircle above, and the radius r has to be large enough to enclose all the singularities that are have positive imaginary parts. Then we apply our residue theorem. So because this is a closed curve integral, according to Cauchy's residue theorem, the value of the closed curve integral is equal to 2 pi I times the residues inside the closed curve. And that's equal to the integral along the line plus the integral along the semicircle here. It turns out the integral along the line, since it's along the real axis, we can substitute now z and understand that our variables are always going to be real. So we can change that to an x. And then here we have our integral along the curve, which we saw will approach infinity as we approach, as r approaches infinity, this integral approaches 0. We had this theorem about zeros and poles and how to find the residues just for your review, and then we had this example problem here which we worked in detail in the video. So that's it for this video. Thank you for watching.